We are now on to our third type of system of nonlinear equations, where we will be looking for the intersection of an ellipse and a circle. So there's a few different scenarios we could end up here. We could end up in here. It's possible that the ellipse and the circle do not intersect each other at all, and we end up with no solution. It's possible that the ellipse and the circle only touch each other at one point, and we have one solution at some point, x1, y1. It's possible that they intersect each other at 2 points, and we get two solutions, which I will call x1, y1 and x2, y2. Or they could touch each other at 3 points, giving us three solutions, x1, y1, x2, y2, and x3, y3. And then finally, they could touch each other at 4 points, say an x1, y1, and x2, y2, a third point of x3, y3, and then a fourth point of x4, y4. So far, we have solved all of our systems of nonlinear equations by substitution. So what I mean by that, looking back at our first example, in step 1, we solved for y, and then we substituted it into the other equation. And then we were able to solve, because then we had an equation that only had x in it. Something similar happened in the second example, where we started off, the equation was already solved for y, and then we substituted it into the second equation, and then we had an equation that only had x in it, and we were able to solve for x. When we're working with a system that has an ellipse and a circle, so notice that neither one of these equations in example 3 are linear. And how do we know that? Because we look at the exponents, right? The highest exponent of x that shows up in both of these equations is 2. X squared. So there's no way that either of those equations are linear, because in linear equations, both x and y show up with exponents of 1, or x and y don't show up at all. So when we're working with a system like this, where there's no linear equation, we will find that it's often easier than substitution is for us to use elimination by addition. So we're going to solve this system by elimination rather than using substitution. So keep that in mind as you work on your assignments. If one of your equations is linear, you're going to want to do substitution, like we did in example 2 and like we did in example 1. But if we're looking at a problem like example 3, where we're seeing these exponents higher than 1 show up in both equations, then we're going to want to use elimination rather than substitution. So the way that we do that is we're going to choose to eliminate a variable, either x or y. I'm going to choose to eliminate x. So I'm looking at the fact that I have an x squared here and a 3x squared here. If I want to eliminate the x's in these equations, I want to manipulate the equation so that I see the same number in front of x, but with opposite signs. The second equation already has a 3x squared in it. So I'm not going to change that equation. I'm going to leave this as 3x squared plus 25 y squared is equal to 100. So ideally, what I want in the first equation is I want a negative 3x squared, so that it has the same number as the second equation, but with the opposite sign. So to get a negative 3x squared, what I'm going to do is I'm going to multiply both sides of the first equation by negative 3. So I'm multiplying the left side of the equation by negative 3, and I'm also going to multiply the right side of the equation by negative 3. So let's do that algebra. We're going to distribute the negative 3. When I distribute it on the left side, we end up with I'll write it over here, a negative 3x squared minus 3y squared. And on the right side of the equation, 26 times negative 3 is a negative 78. I'm not going to change the second equation at all because it already has the positive 3x squared that we want. So now we can see that we do have the same coefficient in front of those x squareds with opposite signs. And the reason that we want that is because now we will be able to eliminate x by addition. So we are doing elimination by addition. So now we are going to add these two equations together. So we're adding like terms, adding the negative 3x squared and the 3x squared, eliminates x and just leaves us with a 0. And we don't have to write that 0, but that is x is eliminated. Now we're going to add the negative 3y squared and the 25y squared to give us a positive 22y squared. And now we're going to add the negative 78 and the 100 to give us a positive 22. And now we have an equation that only has y in it, and we will be able to solve this new orange equation for y. So to solve this equation for y, we're going to divide both sides by 22, which leaves us with y squared is equal to 1. To get rid of the squared on the y, we will need to square root both sides of this equation. And when we take the square root of both sides in an equation, we have to remember plus or minus. So we are left with y is equal to positive 1 or y is equal to negative 1. So we have two possible values for y. Let's see what happens when y is equal to positive 1. So when y is equal to positive 1, I'm going to substitute that back into either one of the original equations. So we had two original equations up here. It doesn't matter which one we pick. I think the first one looks a little bit simpler because the x squared and the y squared don't have coefficients. So I'm working with the equation x squared plus y squared is equal to 26. And I want to know, well, what do we get for x when y is 1? So I'm replacing the y with 1. So I have x squared plus 1 squared equals 26. That's x squared plus 1 is equal to 26. I'll subtract 1 from both sides of the equation to get x squared is equal to 25. Then we square root both sides of the equation to get x is equal to plus or minus the square root of 25, which is 5. So when y was equal to 1, we got two answers for x, positive 5 or negative 5, which means we have two possible solutions here. We have a possible solution of the ordered pair positive 5. That's when x is positive 5 and y would still be 1. Or when x is negative 5 and y could be 1. We will need to check both of those solutions. And we will do that momentarily. Let's go on to check the other case. So we've checked this when y is equal to 1. Let's see what happens when y is equal to negative 1. So when y is equal to negative 1, I'm again going back to this first equation here of x squared plus y squared is equal to 26. I want to know, well, what is x when y is equal to negative 1? I would have x squared plus negative 1 squared is equal to 26. Negative 1 squared is 1. So I get x squared plus 1 is equal to 26, which is the same equation we had earlier. Subtract 1 from both sides to see x squared is 25. And again, we get that x is positive 5 or negative 5 after we take the square root on both sides of the equation and remember plus or minus. So when y is equal to negative 1, we again have two possible solutions. When y was negative 1, x could have been a positive 5, or x could have been a negative 5. And I'm calling them possible solutions because I don't know that they're actual solutions until I check them in both of the original equations. So we need to substitute in to see if we actually do have solutions. So our first original equation was x squared plus y squared is equal to 26. And our second original equation was this equation here, 3x squared plus 25y squared is equal to 100. So we're going to need to check all 4 of these solutions in both of these equations. Let's start up here. So starting with the equation with the possible solution of 5, 1, I'm going to substitute in 5 for x and 1 for y. And I'm asking, does that really equal 26? Well, that's 25 plus 1, which is 26, and so that is a solution. Let's check it in the second equation. That's 3 times 5 squared, because I'm replacing x with 5, plus 25 times 1 squared, replacing y with 1. I want to know, does that really equal 100? 5 squared is 25. 25 times 1 is 25. We're still checking, does that equal 100? 3 times 25 is 75, and 75 plus 25 does equal 100. Go ahead and check both of these solutions here, and you should find that both of these are true. I will quickly show you, because do keep in mind that when you plug in -5 for x in this first equation, one, you do need parentheses around it when you plug in -5. -5 times -5 is a positive 25. And 25 plus 1 is equal to 26. So I've shown that it does work for the equation of x squared plus y squared equal 26. Do make sure to go through the algebra and check that it works for the second equation. You should find that it does. So far we can say that both of these are solutions. You can check the second one once you have verified that it works in the second equation. Let's go down and check the 2 solutions where y was equal to -1 that we have in green. I'm going to plug in the x value of 5 and the y value of -1. That is 25 plus 1, which is in fact 26. So it does work for the first equation of the circle. Let's check it in the second equation of the ellipse. That's 3 times 5 squared plus 25 times -1 squared. That's 3 times 25, which is 75, plus 25, which is 100. So it does work there. So I can go ahead and say that 5, -1 is in fact a solution. Let's check this last point of -5, -1. So we're plugging in -5 for x and -1 for y. That's 25 plus 1, because when you square a negative number, you do get a positive number. 26, so that is equal to what we expected it to be equal to. That is true. Let's check the second equation. So we have 3 times, replace x with -5, plus 25 times, replace y with -1. So 3 times 25 plus 25 times 1 is 75 plus 25, which does in fact equal the 100 that we were expecting. And so we have verified that the point -5, -1 also satisfies both equations. Finally, the last thing I will verify is that if I were to graph both of these original equations in Desmos, we should see a circle and an ellipse that intersect each other in 4 points, and those 4 points should be the same 4 answers we found over here in our black boxes, and that has been confirmed.